Alright, episode 2. So this episode we're going to cover the concept of a matrix. So we're going to look at a matrix as a way of describing a linear transformation using its basis. So first off, we're going to cover what the definition of a basis of a linear transformation is. Then we're going to move on to figuring out bases of specific transformations. And then we're going to look at how we use matrices to represent linear transformations using their bases. Okay, so as before, we took linear transformations and we broke them down into their general forms. So just here we have t, this one-dimensional linear transformation. We saw that t of x is equal to t of x times 1, which is equal to x times t of 1. Here we can see that t of 1 is actually what defines this basis. Or sorry, t of 1 is actually what defines this transformation. And so we say that t of 1 is the basis of t. Similarly, when we were looking at linear transformations from 2 dimensions, we saw that t of xy is equal to x t of 1, 0 plus y t of 0, 1. And so these two numbers here, in this case, t of 1, 0 and t of 0, 1, these together form the basis of t here. Now, in general, what the basis of t actually is just an ordered list of vectors. So here we have some general linear transformation where the basis of t is this series of vectors here, just this list here of t0, t1, t2, t3, all the way through to tn. And so what that means is that t is a linear transformation that has here these variables, so x0, x1, all the way through to xn, and it transforms that vector simply into the combination x0 times t0, which is this here, plus x1 times t1, so x1 times t1, x2 t2, x3 t3, all the way through to xn tn. And so if we had a transformation u whose basis was, for example, 3, 2, then u would transform xy, or if you prefer x0, x1, into x0 times 3 plus x1 times 2, because you can see these here is effectively, this is your t0 and your t1. Okay, so with that in mind, let's jump up a bit, try and figure out the bases of these transformations. So let's look at some specific cases. And then we'll come back up here to some more general cases to try and figure out their basis. Okay, so here we have a transformation from 2 dimensions to 1 dimension, where t of xy is 3x minus 4y. So here t takes xy to x times 3 plus y times negative 4. And so we would say that the basis of t is 3, negative 4, just like that. Okay, well, how about this transformation down here? Here we have that t takes xy, well, I suppose I can just write it up here. T takes xy to this, which you can see is actually 2x, 3x, x, like that, plus negative y, y, 0, which you could also write as x, 2, 3, 1, plus y, negative 1, 1, 0. And so you can see here, just like up here, we have that the basis of t is the list of vectors 2, 3, 1, negative 1, 0, 1. Okay, so what about this one down here? With this one down here, we have t, a linear transformation, taking a point in 3 dimensions, x, y, z, into a point in 2 dimensions, 2x minus y, 3x plus y minus z. So here, we can split this apart into 2x, 3x, plus minus y, y, plus 0, negative z, which you could also write as x, 2, 3, plus y, negative 1, 1, plus z, 0, negative 1. And so that means that here, the basis of t is equal to the list of vectors 2, 3, negative 1, 1, and 0, negative 1. Okay, so now that we've got that down pat, let's move up and try and crack some of the more general forms. So let's say that t is a transformation from the real numbers to the real numbers. Then what is the basis of t? Well, t here maps x to t of x which we've seen is equal to t of x times 1, which is x times t of 1. And so here we have the basis of t being equal to the list, which is just t of 1. So we've got this one output here. Okay, so how about a two-dimensional case? How about a linear transformation t going from 2 dimensions to 1 dimension? Well, we've got that t takes xy to x times t of 1, 0 plus y times t of 0, 1. And so here we have that this here is the basis, this pair of vectors here, because we have our first one times this first vector and our second one times this second vector. So therefore, the basis here of t is going to be equal to the list of vectors t, 1, 0, t, 0, 1. Okay, how about this one here? So here we have t as a transformation from r to r squared, and we actually have the same basis here because t of x equals x times t of 1, but in this case, while we still have that the basis of t is the list containing only t of 1, we now have that t of 1 is actually a two-dimensional vector. Similarly down here, with our transformation from r squared to r squared, or from two-dimensional space to two-dimensional space, we still have that t of xy equals xt of 1, 0 plus yt of 0, 1, but now these two here are actually two-dimensional. So these are actually vectors because t maps from 2 dimensions to 2 dimensions. So now the basis of t is equal to t of 1, 0, t of 0, 1, and these are actually vectors now instead of up here where they were scalars, because here you can see that t maps from r squared to r. Okay, brilliant. So if we come down to here, let's just say we have these three here. Now if you feel comfortable, you might just want to try and convert these into their basis forms first, and then after that we're going to go and try and convert them into their matrices, and then I will show you the answers on the right. Okay, so let's take, for example, this transformation up here. Okay, so I will copy that, paste it down here. Now we can see that this here is equal to x times 2, 3, 1 plus y times -1, 1, 0. And so just as we showed before, the basis of t is equal to the list 2, 3, 1, -1, 1, 0. And how we're actually going to define a matrix is, instead of writing this basis as a list to show what this linear transformation does, we're going to say that the matrix of t is going to be equal to 2, 3, 1, -1, 1, 0. So instead of writing these as a list, we're just going to write them in a grid where the columns, left to right, are actually just our basis vectors in a list. And so that means that here we say that t, linear transformation t, is equivalent to the matrix 2, 3, 1, -1, 1, 0. Okay, now have a go on this side here, just trying to convert each of these three transformations here into their corresponding matrices. And I'll give you 5 seconds, and then after that I will show you the answer on the right. So just pause the video if you want to attempt this. Just realized that my editing software is probably going to cut out the silence, so I don't know whether you're actually going to have 5 seconds, so I'm going to talk for a bit. Okay, so these here are the matrices that you're going to end up with. So here you can see that the matrix here for t is going to be 3, 4, and if you look at the columns here, we've got 3, which is our first basis vector here, and 4, which is our second basis vector here. Similarly, for m of u, we're going to have 3, 2, which is our first basis vector here, and of course that's 3, 2 over here in our matrix. 0, -1, because we've got no y's and -1 y here, and -1, 1, because we've got -1 z here and 1 z here. Same for v, 0, 6, 3, 1, and that's actually what you get when you simplify this here, because we're going to end up with 3y 2x plus y, which of course is going to split apart into, sorry, this is a 6 here because the 2 gets multiplied, 6x, yep, like that. And so here you can see that our x vector here, 0, 6, because there's 0, 6, and y being 3, 1. Fantastic. So, matrix multiplication by a point. So the reason that matrices are actually so useful is because we can take a matrix here, so let's say we took this matrix representing this linear transformation, And we define matrix multiplication by a point by simply saying that a matrix here, 2, -1, I should just copy it. Well, I suppose we say that the matrix of T multiplied by some point, so here we would have xy, is actually just the same as taking T and transforming that point, so xy. So here you can see that the basis vectors of T are these columns here, and so T would take xy and map it to the point x times the first basis vector of T, which in this case is our left column, 2, 3, 1, plus y times the second basis vector of T, which is this right-hand column, -1, 1, 0, right? And that will give us 2x minus y, 3x plus y, x. And so that would be the result of putting xy through this transformation. And so here, if we were to take this matrix and multiply it by a point xy, then what we actually get is x times this first column and y times this second column, because that's exactly what this transformation does. And of course, we must have that the matrix and this transformation are doing the same thing, because our matrix here is just another way to represent our transformation. So therefore, we can say that this is equal to x times our first column, which is 2, 3, 1, plus y times our second column, which is -1, 1, 0. And of course, if we were to simplify that, we would get x times 2, so 2x minus y on the top, 3x plus y, and just x on the bottom. And so you can see here that we've got the same result, whether we use the matrix multiplication or just the simple transformation, because you can see these two results are the same. And so that's how we define matrix multiplication by a point. So you can use that and just play around if you like, show that these matrices here and these transformations give you the same values, and then we will move on to matrix multiplication by other matrices. So given that, so let's suppose that we have here two linear transformations. So we have T that maps 2 dimensions to 3 dimensions and U that maps 3 dimensions back to 2 dimensions. Then it's actually possible for us to take some 2-dimensional vector, xy, shove it into T, which it then spits out some vector in 3 dimensions, some 3-dimensional vector here. We can then shove that into U, and that's going to spit out some 2-dimensional vector here. So we're going to get some final 2-dimensional vector over here. And so that means that there's actually some way of composing these two operations. So first we take T and then we take U of whatever goes in. And so just as we would compose functions together, there's a way of taking U of T, which is U composed of T. So T, we would have this equals U of T of X. Okay, so here we have that the basis of T is 1, 2, -2, 3, -1, 1, and the basis of U is 1, 0, 1, 1, 2, -1. And so here we can see we have two basis vectors, so we must be going from 2 dimensions into 3 dimensions, because these are 3-dimensional vectors. And with U, we go from 3 dimensions, because we have 3 basis vectors, into 2 dimensions, because each of these vectors are 2-dimensional. Right, so if we were to take U of T of some 2-dimensional vector xy, what that is going to give us is U of whatever T of xy is. And so we can use the basis here to see that T of xy is going to be x times, I'll use red up here so we can keep track of stuff, 1 to -2 plus y times our second basis vector, 3, -1, 1. And of course here you can actually see that this is just going to distribute. Just like when we had x times 1, 0 plus y times 0, 1, we can just distribute U over this addition and move the x's and the y's outside. So this is going to be equal to x times U of this basis vector here, plus y times U of this basis vector here. Cool. Now, what that means is that if we want to find the linear transformation which corresponds to this composition U of T, all we actually have to do is take the basis of T here and transform each of these vectors by U. So we transform all of these vectors by U. So let's do that. Actually, I think I'll leave this here and I'll just give us some extra space below. Fantastic. So now we know that the basis of U of T is actually just going to be the basis of T, but we're going to transform each of T's vectors, each of T's basis vectors, so 1, 2, -2, and 3, -1, 1. We're just going to transform all of these by u individually. Okay, so what do we get here? Well, this first vector here, u of 1, 2, -2, that's going to be one lot of 1, 0, two lots of 1, 1, and -2 lots of 2, -1. So this here is going to be two lots of one lot of 1, 0, sorry, which is going to be 1, 0. Then we're going to have two lots of 1, 1, so that's going to be 2, 2, and -2 lots of 2, -1, which is going to be -4, 2. And so you can see that this vector here is going to be -1, 4. So our vector here is, got that correct? Yep, should be -1, 4. Now on this side, we're going to have that u of 3, -1, 1. Just the same, we're going to take 3 times 1, 0 on the left, so that's going to be 3, 0. We're going to take -1 times 1, 1, which is going to be -1, -1. And we're going to take one lot of 2, -1, which is going to be 2, -1. And so that's going to become, if I go down a bit, that's going to become here on the top, 4, -2. So therefore we have that the basis of u composed of t is -1, 4, 4, -2. Fantastic. And so this is the idea that we're actually going to use to multiply matrices by each other, because matrix multiplication, so the matrix of u times the matrix of t, is actually just going to be u composed of t. So let's do that. We're going to take this up here, we're going to convert them into matrices, we're going to multiply them together, and we're going to see that we get the same result. Okay, so here we know that the matrix of t is going to be 1, 3, 2, -1, -2, 1, and that the matrix of u is going to be equal to 1, 0, 1, 1, 2, -1. Okay, now we take m of u times m of t, which is going to be 1, 0, 1, 1, 2, -1, times 1, 3, 2, -1, -2, 1. Okay, so just as before, we have u acting on the basis vectors of t. So how we're going to do this is we're just going to take this first column vector here, so this is our first basis vector of t, and we're going to transform it by u using these vectors here. So for our first column here, we're going to take 1 times 1, 0, plus 2 times 1, 1, plus -2 times 2, -1. Okay, so that's going to give us 1 to -4. So on the top here, we're going to have -1. And on the bottom here, we're going to have 3. Oh, can I not do addition? We're going to have 4 on the bottom. Sorry, 4 on the bottom. Because here we have 0, 2, and -2 times -1. So that's another 2 on the bottom. Okay, cool. So we can see that our left-hand side is going to be -1, 4, because that is what you get when you take this here, which is going to be our first basis vector of t, and you transform under u, just like we did up here, which is the first basis vector of t transformed under u. Okay, so secondly, we're going to take this second vector here, and we're going to transform that under u as well. So when we transform that, we're going to take 3, so let's just say this is the first column and the second column. So here we're going to take 3 lots of 1, 0, -1 lots of 1, 1, and we're going to take 1 lot of 2, -1. Of course, if we add this up together, we get 4 minus 2. And so here we have, that bracket shouldn't be there, 4 minus 2, and so our right-hand side is 4 minus 2. And so you can see that this matrix here, our left here, this is going to be our first basis vector, -1, -4 of u of t, and our right-hand side here is 4 minus 2, which is this second vector of the basis of u of t. Okay, so therefore the matrix of u of t is equal to -1, 4, 4, -2, and the basis of u of t is -1, 4, 4, -2. And so you can see how the matrix here, this matrix of u of t, is actually just the compact representation of the transformation. So here we could even say that u of t takes xy to x times the first of its basis vectors, -1, 4, plus y times the second of its basis vectors, 4, -2. Okay, so let's just go through some more matrix multiplications together, just so we can get the hang of it. So let's try, say, 1, 0, 2, 1 times 2, 1. How about this? Okay, so here we have this here, which could be viewed as a transformation from 1 dimensions to 2 dimensions, if you like, or simply as a point in 2 dimensions, and we have this matrix here. So here we're going to take two lots of our first column and one lot of our second column, because this is our first basis vector and this is our second basis vector, and we're transforming this point. So we've got two lots of our first basis vector and one lot of our second one. So this is 2 times 1, 2 plus 1 times 0, 1, which gets us 2 plus 0, so 2 on the top, and 4 plus 1, so 5 on the bottom. Okay, so similarly, if we were to do 3, 1, 0, negative 1, 2, 4 by 1, 0, 2, 1, then this here is a transformation from 2 dimensions to 3 dimensions. And so we take this point here, which is the first basis vector of our transformation on the right hand side, and we apply this transformation here to that basis vector. And so that gives us that the right hand side of this matrix is going to be 1 times this first vector plus 0 times the second vector, which is just going to be this first vector. So our left hand side is going to be 3, 1, 0. And then for the right hand side, we see we're going to have 2 times our first basis vector and 1 times our second basis vector. So that's going to be 6, 2, 0, which is 2 times our first basis vector plus 1 times our second basis vector, which is going to be negative 1, 2, 4, which is of course going to be 5, 4, 4. And so that would be the result from multiplying these two matrices together.